Good afternoon everybody. So today my topic is orbital concept of covalent bond. So before describing the orbital concept of covalent bond, let's have a brief description of bond. Chemical bonds, when two atoms are joined together by a chemical linkage, that is chemical bond, and covalent bond is when there are the atoms are joined together by sharing their electrons, that is covalent bond. So chemical bond is force of attraction between which holds the constituent atom together is called a chemical bond. So when atoms are joined together by a chemical linkage, that is a force of attraction that is chemically that join the two atoms chemically, that is chemical bond. And covalent bond is bond formed by the mutual sharing of electrons between the combining atoms, that is covalent bond. When atoms combine with each other by sharing their electrons, that is chemical bond. So examples of covalent bond is for example formation of hydrogen molecule. Hydrogen atom has one electron only. In the formation of H2 hydrogen molecule, two atoms of hydrogen contribute one electron each for sharing and occurring the configuration of helium. So you are seeing the picture here. So here each hydrogen atom has one electron each, and they are joined together to form and sharing their one electron each and forming a covalent bond. So the bond formed by sharing of electron is a covalent bond. Another example is formation of oxygen molecule. So in oxygen there are 8 electrons, and in valence shell there are 6 electrons. 2 electrons are half filled and they join together, and they are sharing these 2 electron of each oxygen and form oxygen molecule. So the figure shows below is oxygen molecule, in which one oxygen, you can see the picture here. So in valence shell there are 6 electrons, and in ground shell there are 2 electrons, and the 4 electron of 2 oxygen form covalent bond. Formation of HF molecule, that is hydrogen fluoride molecule. More example of covalent bonds are here. So formation of HF molecule, in hydrogen there is 1 electron, and in fluorine there are 7 electron in valence shell, and the half filled electron of hydrogen share with half filled electron of fluorine and form covalent bond. So more examples of covalent bonds are chlorine chlorine, that is chlorine molecule, hydrogen fluoride molecule, water, ammonia and methane. So in each of these molecules the bond is formed by sharing of electron, that is covalent bond. General characteristics of covalent compounds. Covalent compounds are non-polar nature. These compounds don't form ions and are thus non-ionic in nature. Low melting and boiling points. So the covalent compounds are mostly liquids or gases at room temperature. Due to weak intermolecular forces, these have low melting and boiling points, because the intermolecular forces in these molecules is low. That is the force that is in between two molecules, that is low. So due to these low intermolecular forces, melting and boiling point of this molecule is low. For example, they are mostly liquids. The physical state of this is mostly liquid. So due to these they have low melting and boiling points. Electrical conductivity, they don't conduct electricity in fused state or in solution, because they don't have ions. Electricity is conducted when ions move or when charge move. So in covalent compound there is no ion formation, so they don't conduct electricity in fused or solution. Solubility, soluble in organic solvents and slightly soluble in water, because they are non-ionic nature and they don't have any charge. So, they are soluble in organic solvents and slightly soluble in water. The bond is rigid and directional and thus give rise to space isomerism. In ionic bond, the bond is not directional, but in covalent bond is directional, and so it gives rise to space isomerism. That is, there are different geometries for the molecules due to the rigid bond formation. The compounds undergo molecular reactions which are incomplete and usually complex. Covalent compounds undergo molecular reactions, so they don't undergo substitution reactions. So, they undergo molecular reactions which are incomplete and usually complex. There are two theories to explain covalent bonding. These are electronic theory of covalency or Lewis concept, and another concept is orbital concept. So, first one is electronic theory of covalency. This is also called a Lewis concept. Second theory is orbital concept. Here we are here to discuss only orbital concept. Lewis concept or electronic theory of covalency. According to this theory, a covalent bond is the force of attraction which arises due to mutual sharing of electrons between the two atoms. This type of bond is formed between two similar non-metallic elements, for example AA or BB, or dissimilar atoms. So, according to the first point of this theory, covalent bond is formed by the mutual attraction which arises due to mutual sharing of electron. So, due to sharing there is attraction. According to this theory, the bond formed between two non-metallic elements, similar or they may be dissimilar. Both the atoms A and B are short of one or more electrons than the next noble gas configuration. For example, in oxygen is two electron less than noble gas. That noble gas is next to oxygen is neon. So, oxygen has 8 electrons, which is 2 less electron than neon, and fluorine has 1 electron less than neon. If both the atoms share one or more electrons, the shade pair becomes their common property. As a result, both of the atoms acquire noble gas configuration. So, they share electrons to occur noble gas configuration. If both the atoms share 1, 2 or 3 electrons each, single, double or triple covalent bond is formed respectively. For example, hydrogen share 1 electron. So, in hydrogen there is a single bond, and in oxygen 2 electrons are shared in by 2 electrons are contributed by each atom, and there is formation of a double bond. And in nitrogen 3 electrons is contributed by each nitrogen atom, and there is formation of a triple bond. The number of electrons contributed by an atom for sharing to form a covalent bond is called covalency. The number of electrons that atoms share is called covalency. If hydrogen share 1 electron, then its covalency is 1. If oxygen share 2 electron each, then its covalency is 2. If nitrogen share 3 electron, its covalency is 3. one shade pair of electron, single bond, for example hydrogen, 2 shade pair of electrons, double bond, for example oxygen, 3 shade pair of electrons, nitrogen, triple bond. Generally bond distances decreases as we move from single through double to triple bond. So, nitrogen, so which of these 3 has least bond distance? So, this is nitrogen. Nitrogen has least bond distance. Limitation of Lewis-Langmuir concept. This concept failed to explain how the atoms are held together in the molecules like hydrogen, chlorine, etc., in which there are no ions and hence there are no electrostatic force of attraction. The shapes of molecule containing covalent bond. So, this concept does not tell about the shapes of molecule. The release of energy during the formation of covalent bond, because it tells that only sharing is here in covalent bond. So, it does not tell about the release of energy. There are two theories to explain these limitations. These are valence bond theory, orbital concept, and molecular orbital theory. Orbital concept of covalent bond. This is also called valence bond theory of covalent bond. This theory was put forward by Hitler and London in 1927 and further developed by Pauling and others. According to this approach, a covalent bond is found by the partial overlap of two half-filled atomic orbitals containing electrons with opposite spins. So, covalent bond is found by partial overlap of two half-filled atomic orbitals containing electrons with opposite spin. For example, formation of hydrogen molecule on the basis of this concept. Hydrogen atom has only one electron which is present in 1s orbital. The nucleus of each hydrogen atom attract the electron cloud of other hydrogen atom. In this way, the two hydrogen atoms start approaching each other. So, the figure is shown here. So, hydrogen atom has only one electron which is present in 1s orbital. So, the two atoms of hydrogen each having one electron in 1s orbital. So, the orbital approach each other and overlap and form covalent bond. A stage comes when the electron clouds of hydrogen atom partially merge with each other or overlap. This overlapping results in the release of some energy and the formation of strong covalent bond between two hydrogen atoms as shown above. So, the overlapping, when they merge with each other, when the orbital merge with each other, so this resulting release of some energy, and the energy released makes bond stable. Bond is found when the energy is released. Formation of hydrogen fluoride molecule on the basis of this concept. So, here one hydrogen orbital, electron of hydrogen is in 1s orbital and the valence single electron of fluorine is in 2p orbital. Here 2px is shown. So, the orbital of hydrogen approaches with 2p orbital of fluorine. So, the single electrons from both the sides is shared. The orbital of 1s orbital of hydrogen and 2p orbital of fluorine is are overlap with each other and they form covalent bond. Partial overlap. Part of electron cloud of each of the two half-filled atomic orbital becomes common. So, what is partial overlap? So, when the here is shown partial overlap. So, partial overlapping is when part of electron cloud of each of these two half-filled atomic orbital becomes common. The strength of the bonds depend upon the extent of overlapping. The more is overlapping, the more is strength of bond. The more strong is bond. Less is overlapping, the bond is not strong, bond is weak. Greater the overlapping, stronger is the bond. Also, according to Pauli's exclusion principle, that an orbital cannot have more than two electrons and must have opposite spins in order to minimize the force of repulsion. So, two atomic orbitals at the time of overlap will have opposite spins. Types of overlapping and nature of covalent bonds. Strength of bond is determined by the extent of overlapping. Larger the overlapping means stronger the bond, more energy is released when bond is formed and more energy is needed to break the bond. Extent of overlapping is determined by the nature of atomic orbitals and the way in which they overlap each other. Types of overlapping nature of covalent bond. Depending upon these factors, covalent bonds are classified into two types, sigma bond and pi bond. So, depending upon the overlapping, there are two types of bond, sigma and pi bond. So, sigma bond is when two half-filled atomic orbitals overlap at internuclear axis, the bond formed is called sigma bond. So, when they overlap at internuclear axis, that is at axis at which there is overlapping, the axis that join two nucleus. When they overlap at that axis which join nucleus, that is sigma bond. Example is SS overlapping. Sigma bond is found by one of the following types of overlapping: SS overlapping. The mutual overlapping of half-filled s orbitals of two atoms always leads to the formation of sigma bond. For example, hydrogen molecule. So, here the overlapping is on internuclear axis. The SS overlapping means when two half-filled s orbitals overlap. So, both the overlapping orbitals are here s orbital. So, s orbital is spherically symmetrical, and as the shape of the s orbital is spherical symmetrical, when they overlap each other, so the overlapping is at internuclear axis and the bond formed is sigma bond. Another example is sp overlapping. Another type is sp overlapping, the bond formed by overlapping of half-filled s orbital of one atom and p orbital of another atom is again a sigma bond. For example, hydrogen fluoride molecule. Here s orbital of hydrogen is overlapping with p orbital of fluorine, which is p orbital, and sp overlapping at internuclear axis is a sigma bond. Next is pp overlapping at internuclear axis. When the partially filled p orbitals of two atoms get close enough to overlap each other along with internuclear axis, the bond established in this way is sigma bond. For example, fluorine-fluorine molecule. So, when the two fluorine molecule which has p orbitals, so when they overlap with each other at internuclear axis, so this is a sigma bond. This is called pp overlapping. Before this was sp overlapping, and this is ss overlapping, this is pp overlapping. So, due to the maximum overlapping taking place in the formation of bond, these bonds are quite strong. The single bonds present in all the molecules are always a sigma bond. So, when there is only a single bond, that must be a sigma bond. So, the different types of sigma bonds are shown here: SS overlapping, sp overlapping, and pp overlapping. When two half-filled p orbitals overlap sideways, that is lateral overlap, the bond formed is called pi bond. So, another type of bond is a pi bond. When two half-filled p orbitals overlap sideways, that is they do not at nuclear axis, but overlap at both sides of internuclear axis, this is called pi bond. The electrons participating in the formation of pi bond are called pi electrons. As both the lobes of the p orbitals are involved in the sidewise overlap, the same pi bond is formed above and below the internuclear axis. Because the lobes of p orbitals are involved in sidewise overlap, that is both the lobes of p orbital are involved, the same pi bond is found above and below the internuclear axis. Here pi bond is shown. Pi bond is found between two atoms which are already linked to each other by sigma bond. Pi bond is formed only in presence of sigma bond. The two lobes of two p orbital is shown for one atom, and they overlap with another p orbitals with according sideways. So, remaining p orbital from sp or sp2. So, for formation of pi bond, planar molecules, each carbon is trigonal planar with pi cloud above and below the plane. So, formation of pi bond. Pi bond hinder rotation about the carbon to carbon bond. As carbon carbon is linked from both the sides, so they cannot rotate against each other. So, pi bond hinder rotation about the carbon to carbon bond. So, planar molecule, each carbon is trigonal planar with pi cloud above and below the plane. Comparison of relative strength of pi and sigma bond, sigma and pi bond. The strength of a covalent bond depends upon the extent of overlapping. Greater the overlapping, more is the energy released and stronger is the bond formed. That is, strength of covalent bond depends upon the extent of overlapping. More the overlapping will be, when overlapping is more, the energy released will be more and the bond will be stronger. Since the axial overlapping is greater as compared to sidewise, a sigma bond is stronger in comparison to a pi bond. The relative strength of three types of sigma bond is, in sigma bond, when SS overlapping, there is a strong sigma bond as compared to SP, and that will be strong as compared to PP overlapping. Concept of hybridization. Generally, the covalent bond is formed by an atom equal to the number of unpaired electrons in it, but the atoms of beryllium, boron and carbon are an exception to this generalization. So, another concept is hybridization. Generally, the covalent bond is formed by an atom equal to number of unpaired electron in it, but beryllium, in beryllium there is no unpaired electron, but it forms two bonds, and in boron there is one unpaired electron, but it forms three bonds, and in carbon there are two unpaired electrons, but it forms four bonds. So, concept of hybridization, due to concept of hybridization, it will have to be described that they form 2, 3 or 4 bond. The electron configuration of the elements are, the atomic number of beryllium is 4, electron configuration 1s2, 2s2, boron atomic number 5, electron configuration 1s2, 2s2, 2px1, and for carbon atomic number 6, electron configuration 1s2, 2s2, 2px1, 2py1. From this configuration, beryllium should be inert, boron monovalent, and carbon should form divalent compounds, but they form beryllium difluoride, boron trifluoride and methane. To explain these, electron configuration is modified and electrons in valence shell are promoted to vacant orbitals in vacant shell. This process is called promoting the electrons. So, to explain the no need of energy to promote an electron and identical nature of all the bond formed in molecule, we have a concept of hybridization. Hybridization is defined as the phenomenon of intermixing of orbitals of slightly different energies so as to redistribute the energies and give rise to a new set of orbitals of equal energy and shape. The new orbital formed are called hybrid or hybridized orbital. So, in hybridization, the hybrid means intermixing. So, this is the phenomenon of intermixing of orbital. When orbitals of different energies, that is slightly different energy, are intermixed, they redistribute the energy redistributed, and they give rise to a new set of orbitals of equivalent energy. So, the number of orbital is equal to the number of orbital intermixing. So, these new orbitals have equivalent energy and shape. So, these are called hybrid orbital. Characteristics of hybridization. Hybridization takes place between the atomic orbitals of same atom having approximately equal energy. Hybridization takes place between half filled as well as completely filled orbitals. That is, it is taken place between half filled as well as completely filled. But in covalent bonds, there are only half filled orbitals are involved. The number of hybrid orbitals formed is equal to number of orbitals that get hybridized. How many number of hybrid orbitals are formed? Equal to the number of orbitals that get hybridized, that is, that are intermixing. The hybrid orbitals are always equivalent in energy and shape. So, all the orbital, whether it is s or p, d, so they all have different same energy after intermixing. The orbitals, hybrid orbitals are directed in space in some preferred directions. All the orbitals of the valence shell may or may not take part in hybridization. So, all the orbitals of valence shell that may or may not take part in hybridization. Types of hybridization. Hybridization is of different types depending upon the nature and number of orbitals taking part in hybridization. For example, hybridization involving s and p orbitals. So, there are three types: mixing orbital when mixing orbital are s and p. So, hybridization sp3 when 1 s and 3 p are mixing. So, hybridization is sp3 when 1 s and 2 p are hybridizing. So, the hybridization is sp2 when 1 s and 1 p is being hybridized. The hybridization is sp. So, according to the orbital that are intermixing, we have hybridization sp3, sp2, sp3 or little or tetrahedral hybridization when 1 s and 3 p orbitals of same shell of an atom mix to form 4 equivalent orbitals. So, there is sp3 hybridization. The new orbitals formed are called sp3 hybrid orbitals. These orbitals are directed towards the four corners of a regular tetrahedron, making an angle of 109 degree and 28 with one another. That is, all the orbitals, all the hybrid orbital are at angle 109 degree 0.28. So, each sp3 hybrid orbital has 25% s character and 75% p character. As there are 4 types of orbitals, 1 s and 3 p. So, 4 types of orbital each has 25% character. So, in sp3 1 is s orbital and 3 are p orbital. So, 3 p orbital has each 25% character, has 75% character. So, p character in hybrid sp3 orbital is 75% and s character is 25%. So, the tetrahedral figure shown below has 4 orbital, each orbital is sp3. So, each orbital is sp3, each orbital has 75% p character and 25% s character, and the shape is called tetrahedral. So, sp3 hybridization is also called tetrahedral hybridization. So, this is sp3 hybridization, shape is tetrahedral, s character 25%, p character 75%. So, when 1 s and 3 p orbitals are hybridizing, so the hybridization is sp3, shape tetrahedral, and s character 25%, p character 75%. sp3 hybrid orbitals in methane. In methane, there is carbon and 4 hydrogens. So, the electronic configuration of carbon is 1s2, 2s2, 2p1, 2px1, 2py1, and in valence shell there are 4 electrons, 2 electrons in 2s orbital and the another 2 electrons are singly filled in p orbital, 2 p orbitals, one is in 2px and another is in 2py. So, they hybridized to form